Chapter 5, Work Energy Power. This chapter is largely the same as what you have done in the O levels. No new concepts are introduced. The main concept is still the principle of conservation of energy. What are the primary differences? In O level, the direction of force and distance moved are in the same direction. In the A level, now the direction of the force and distance moved can be in different directions. Energy is the ability to do work. Let's consider the example of a toy car. Nowadays, toy cars are powered by batteries. In the past, toy cars are powered by spring. In order for the toy car to move, the spring has to be wound up. A wind-up spring has the ability to do work. Energy is a scalar quantity. It has magnitude but no direction. The unit for energy is the joule. The joule is a derived unit consisting of the base SI units of kilogram meter square per second square. Let's briefly talk about some of the forms of energy you will encounter in the H2 physics course. In this chapter, you will discuss about mechanical energy. We will look at kinetic energy, which is the energy of a mass due to its motion. We will also look at potential energy. In particular, we'll look at gravitational potential energy and elastic potential energy. In the later chapters, you will encounter electrostatic potential energy, which is due to the presence of charge. Okay. We'll look at chemical energy, which is the energy released due to a chemical reaction. Sound energy, which is energy transmitted by sound waves through the vibration of particles of the medium. We also look at thermal energy, energy transferred from one place to another due to a temperature difference between the region. In thermal physics, you will also look at internal energy, which is the sum of kinetic energy of the molecules due to random motion, and also potential energy due to intermolecular forces between the molecules. You will also look at radiation energy and nuclear energy towards the end of the syllabus. One of the most important principles is the principle of conservation of energy, which states that the total energy of an isolated system remains constant. Energy can be transferred from one form to another, but never created nor destroyed. This means, in an equation form, the total energy of an isolated system before a process will be equal to the total energy of the isolated system after the process. An isolated system refers to a system that does not allow the transfer of either thermal energy or mass to and from its surroundings. We now watch a short video segment of Professor Walter Lewin from MIT conducting his famous experiment of the principle of conservation of energy.
I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0.
And this is what happens if the experiment is performed incorrectly. Let us consider some examples of the principle of conservation of energy. A. Burning of fossil fuels. Oil, coal, and wood are examples of fossil fuels. They are made up of chemical energy. When they are burned, the chemical energy will be converted into light, sound, or thermal energies. Some of these may be useful, some may be regarded as useless. B. A body falling through a viscous fluid. When the body is released from rest in a fluid, it has gravitational potential energy. As it falls through the fluid, some of the gravitational potential energy is converted into kinetic energy, and some of it is converted to work done by the drag forces. C. A car stopping when the brakes are applied. The kinetic energy of the car is converted into thermal energy in the brakes. B and C is important because they are part of the H2 syllabus. What is the relationship between energy and work? Work is actually essentially a process or means by which energy is transferred. Work done by external forces such as frictional force or an applied force can result in a change in energy, such as kinetic energy, gravitational potential energy, or elastic potential energy of a system.
Let's go to some examples of the relationship between energy and work. In this example, the weightlifter uses chemical energy in his muscles to lift a bar upwards, followed by lifting it downwards. The weightlifter exerts an upward force and displaces the bar upwards. This is equivalent to positive work done on the bar. What is the change in energy? There is an increase in gravitational potential energy, but there's no change in kinetic energy. The weightlifter now uses an upward force to displace the bar downwards. This is negative work done. Again, what are the changes in energy? There is a decrease in the gravitational potential energy, but there's no change in the kinetic energy. Another example of a man pushing a box to the right. The man exerts a horizontal force on the box on a frictionless ground over a distance of x. This is positive work done. What is the change in energy? There is an increase in kinetic energy, but no change in the gravitational potential energy. The last example. girl exerts a force on a stretch band, extending it by x. This is positive work done. The change in the energy. There is an increase in elastic potential energy, but no change in gravitational potential energy and kinetic energy. Now go to the definition of work done by a force. The work done by a force is the product of the force and the displacement of the point of application in the direction of the force. Therefore, the formula work done by a force is equal to force times the displacement in the direction of the force. For work done by a constant force, again, is work done by the force times the displacement in the direction of the force, i.e., force times the displacement cosine theta, that is this resolving the displacement, or if you choose to, you can also resolve the force. Work done equals to force cosine theta multiplied by the displacement x. From the formula, work done is equal to fx cosine theta. If the angle between the force and the displacement vector is less than 90 degrees, the component of the force is in the direction of the displacement x. So that is positive work done. If the angle is greater than 90 degrees, but less than 270 degrees, then resolving the component of F will result in a component being opposite to that of the displacement X. This will be a negative work done. What if it's equal to 90 degrees or 270 degrees? So according to the definition, when angle theta equals to 90 degrees, cosine 90 is equal to 0. Therefore, the work done is 0. Conceptually, since F is perpendicular to displacement x, then the work done by F must be 0, as it is never in the direction of the displacement. Concept check. Is work done in the following scenarios. We have Frankie applying a force to the wall and becoming exhausted. No work is done on the wall. The wall is not displaced. A force must cause a displacement in order for work to be done. What about the case of a satellite undergoing uniform circular motion around the Earth? The satellite experiences a centripetal force that is perpendicular to the displacement at all times. This will be discussed in the chapter on circular motion. No work is done by the gravitational force on the satellite because the gravitational force is always perpendicular to the displacement. Work done by the gravitational force on satellite is force times the displacement cosine 90, which is equal to 0 joules. Let's look at example 1. A man pulls a box horizontally for a distance of 150 meters with a rope making an angle of 25.8 degrees with the horizontal. There is a frictional force of 10 Newton acting between the box and the ground. And the tension in the rope is 40 newtons. Determine the work done by each force acting on the box. The normal practice of solving such an equation is to first draw a free body diagram. Indicate all the forces acting on the box. Choose a suitable axis that is choose a suitable axis that is in the direction of the displacement. In our case, the horizontal direction. The work done by tension. Resolve the tension force along the direction of the displacement, which will be 40 cosine 25.8 degree times 150. So the work done is 5.4 times 10 to the power of 3 joules. Work done by friction. The friction force and the displacement has an angle of 180 degrees. So the work done by friction is F cosine 180 degrees multiplied by X. So the answer is minus 1500 joules. Work done by the normal reaction, N cosine 90 times X. Cosine 90 is 0, so the work done will be 0. Likewise for the weight, work done by weight or by gravity, also 0. Now we consider the work done by a variable force. For a constant force, the work done is given by the formula F times product of the F force and the displacement and the angle in the cosine of the angle theta. For a variable force, the work done is the integral of the force times a small change in the x, delta x, which is equivalent to the area under the fx graph. One example of a variable force is the Hooke's law. It is the force on a spring versus the extension. Hooke's law states that F is equal to kx, where k is the spring constant. The elastic potential energy is the integral of the force dx. which in this case will be just half kx squared, area of the triangle. Work done by a variable force again. In A levels, it is possible that the question requires you to estimate the area under a F versus displacement graph. For the curve in A, for the varying force versus x in A, we are expected to estimate by counting the squares. Or alternatively, you can draw a few trapeziums and calculate based on the area of each and sum up the area of the trapeziums. For B, you are expected to calculate accurately using the area of a trapezium. Example 2. On the axis shown, sketch the corresponding work done versus displacement graph for the graph shown. Solution. From O to A, the force is increasing in value linearly in the force displacement graph. This is equal to the increasing gradient of the work versus displacement graph. From A to B, the force is constant in the force displacement graph. In the work done versus displacement graph, you will have a constant gradient from A to B. The elastic potential energy is the energy stored in a spring or any material that can undergo elastic deformation. For an object that obeys Hooke's law, elastic potential energy equals to half kx squared. Let's consider the case of a spring with a mass attached and the external agent applying a force of Fa. In this case, the gain in the elastic potential energy of the spring is entirely due to the work done by the external agent Fa. To ensure there's no change in Ke, or with the mass attached to the spring moving at constant speed, Fa is equal to Fs, where Fs is the force exerted by the spring on the mass. Since F net then equal to 0, so the A is equal to 0. Hence, within the proportionality limit from O to A, work done by the external agent is the gain in the elastic potential energy of the spring. We integrate the function of F in the limits from O to XA. Otherwise, it's the area under the force versus displacement graph. Area of a triangle is half kxa squared. Beyond the proportionality limit from A to B, work done can be found by counting the squares or the trapezium rule. What if the spring is not attached or not stretched horizontally but vertically? In this case, the gain in the elastic potential energy will not be entirely due to the work done by the external agent. The loss in the gravitational potential energy will contribute to the gain in the elastic potential energy. In general, for the vertical spring, the gain in the elastic potential energy is equal to the loss in the GPE plus the work done by the external agent. Take note that of the formula for the gain in the elastic potential energy. It's the work done is the half kx squared at the second position to the square minus half kx1 to the square.
Let us consider the work done by a gas expanding against a constant external pressure. Let's imagine a situation of a gas enclosed within a cylinder and a piston at a pressure Pi. The environmental pressure is a constant value of P. If we apply some heat to the enclosed gas, keeping the pressure at P, then the piston will displace by X to the right. Assuming the piston area is A, then the work done W against the constant external pressure is equals to the force due to the atmosphere multiplied by X, the displacement. Force is given by the pressure, external pressure multiplied by the area times X. A times X is equal to the change in the volume. So you have the final work done against the constant external pressure is equal to pressure times delta V, change in the volume. This concept will be dealt with greater detail in chapter 9, the first law of thermodynamics. We now do a practice on the work done by a gas. Here we have a gas that is compressed at constant pressure from 1.5 at 1.5 times 10 to the power of 4 pascals. Its volume changes from 1.2 to 0.8 times 10 to the power minus 4 meter cube. Represent this compression graphically and then determine the work done on the gas. For part A, the graph is as shown. The arrow is important. It shows that the process is compression from a higher volume V1 to a lower V2. The work done on the gas, the equation is given by pressure times the change in the volume. Substituting in the values, the work done on the gas is 0.6 joules to 2 significant figure. The work done on gas is positive since this is a compression. If the process had been an expansion, then the work done on the gas will be negative. We will look at this in more detail in the chapter on the first law of thermodynamics. You should now watch a video of how the work done on a gas is converted to the internal energy of the gas. The work done is a positive work done on the air since it is a compression. Hence, the air gains energy, causing the internal energy to rise. The gain in the internal energy is translated to thermal energy of the gas. We will look at this in more detail in chapter 9. We now look at the situation when work done is by the gas, an expansion. Initially, the bottle contains alcohol vapor which is invisible to our eyes. When the pressurized gas air in the bottle is suddenly allowed to expand with the help of the pump, the gas does work to expand against the external pressure and hence loses its internal energy, causing its temperature to drop. The chill in the bottle causes the alcohol vapor to condense into visible alcohol clouds. Again, we'll see the detailed explanation in chapter 9.